So we've covered 3 of 6 parts of my talk on big data. In the 4th part, I want to talk about something that is beyond MapReduce. So if you remember, we said that big data requires a cluster of computers. A cluster of computers requires a specialized software and a method of computing. We said that Hadoop was a great example of it. And then we said we can use something known as MapReduce method to achieve data local operations for big data processing. In the 4th part, I want to touch upon the point I ended with previously, which is that MapReduce is very inflexible. So is there something better that we can do? So first question obviously is, why do we need to think beyond this MapReduce model, which actually, by the way, is very, very successful. You would be amazed at what MapReduce has achieved. It has processed petabytes and petabytes of data in record time. So Yahoo and Google back in 2005, 2006, when they announced how they had assembled this cluster of 1000 nodes and were able to process petabytes of data in just a matter of few hours. It was a very, very big achievement back then, and it continues to remain even today. Anyway, so why beyond MapReduce? So first and foremost, MapReduce was designed for what is known as batch processing. So batch processing essentially means there is a chunk of data and you process it and you hit the enter key, you go for a vacation, you come back, the data processing is done, and then you look at the result. So basically offline processing, non-interactive processing, and MapReduce is fantastic at doing that, which is what I was saying. Google and Yahoo did some crazy quick processing on huge amounts of data. But that's the point. It is not interactive. Sorry, I just dropped my microphone. So what I was saying is that it is not interactive. But data science workflows demand interactive analysis. So what do you do in data science? You look at the data and you say, hey, what does this do? Let me quickly calculate an average of this, average of that, compare the averages. The averages are different. So maybe there is some pattern that I need to worry about. And that is how data science workflows are. They are interactive in nature. And MapReduce is not good for this. And it's also limited. Imagine taking every single program that you could very casually write in Python or C or whatever and having to break it down into map plus reduce, where map has this constraint that it has to be data local or independent of other data blocks, and reduces has to be this. It's inflexible, which is why people started developing something else, and that's something which has become extremely popular today. It is called Spark. So Spark can be best described as an open source analytic engine. So the first thing it does is that it gives you a data structure called RDD, Resilient Distributed Data Sets. It is a data structure which is designed to be one big data set loaded in memory across the RAMs of all the clusters. So unlike in case of Hadoop, where the data is sitting in the individual hard disks, Spark tries to keep the data in the random access memory. And it gives you this RDDs whose job is to take, say, imagine a table, right? A pandas data frame of 500 gigabytes. You cannot load it. But if you have a cluster of machines whose sum total of RAM is greater than or equal to 500 GB, then Spark gives you a way of loading that entire table or data frame into the memory. That is what RDDs do. It also gives you a graph-based computing engine. We won't have time to go into details of this, but the basic idea is you say, hey, let's do A, then I want to do B, then I want to do C, then I want to do D, then I want to do E. What Spark does is it doesn't do any of this. It just makes a graph which represents the sequence of A, B, C, D, E. And then you say, okay, the output. Now Spark says, oh, I have no choice but to process now. Until now, I was only making a list of things to do. Now I really have to do them. That's lazy. That's why I call it lazy evaluation. And it studies the graph that it has made. And it says, you know what? I can combine B and E effectively so that I save some time. And maybe C doesn't even need to be done because D is sort of undoing it. So it does this beautiful analysis of your computations, figures out the fastest way to do the processing, and then processes it. And as I already said, it's in memory, so it's extremely fast. And okay, this is a major typo here. What I meant is it is more flexible than MapReduce. So please read that correctly. The last bullet point here is more flexible than MapReduce, not RDD. Sorry for that error. So it supports many more operations than mere map and reduce, and therefore allows you to do many more things more flexibly. This is what the architecture diagram looks like. So what is amazing about Spark is that it can happily talk to Yarn. It can also work on your laptop. That's what standalone means. There is also a cluster called Mesos cluster, which is slightly different from Yarn. It is also a method of doing big data. But you see, Spark core, the core engine of Spark, is designed to nicely communicate with your existing Hadoop cluster based on Yarn or any other cluster as well. So it is very flexible. And its main job is to give you these RDDs whose job is to represent a data set in a distributed manner, in a very in the memory, that is. And then it says, I'm going to give you 4 interfaces to work with the RDDs. I'm going to give you something called streaming analytics, so that if your problem is that your data is streaming in, and as and when the data comes in, you need to keep processing it, I'll give you a way of using RDDs for that situation. I will give you Spark SQL. So for those of you who don't know, SQL is this beautiful language where instead of saying do this, do this, do this, you can say, hey, give me an average, then the computer figures out how to calculate it. So it's a very declarative language as opposed to being imperative. And Spark SQL basically says, you want to perform SQL operations on my RDDs? Sure. Give me your SQL statement. I'll figure out how to convert them into low-level operations. Then there is GraphX, which is designed for what is called graph processing. Again, no time to go into that, but very beautiful field of study, which is graph theory. So you want to do graph operations, graph library is available, and of course there is machine learning library to do machine learning operations on RDDs. And then all of these can be accessed using a common interface called Data Frames API. If you are an R programmer, use R. And remember, it was in Scala that Spark was written in. So Scala obviously can be used. You can use Java, you can use Python. Any of these languages can be used to access the Data Frames API. And from the Data Frames API, these are the 4 things that you can do. And the Spark core engine in turn is flexible. It can sit on multiple clusters, different kinds of clusters. Now the question is, so should I just throw away MapReduce and use only Spark? That is not correct. There is a choice you need to make. Should you try and do your work with MapReduce, or should you do everything in Spark since Spark is bigger, better, faster and more flexible? Well, here we can invoke a theorem called the SCV theorem, speed, consistency and volume. So speed basically refers to how fast do you want to process the data. Consistency means that your result should be deterministic. Now you would say all results are deterministic. No. Suppose I want to calculate the average of 10 billion numbers. There are 2 ways. I could strictly calculate the average of 10 billion numbers, or I could take a subset of 1 million, sample 1 million out of 10 billion and calculate the average. Now, if I am going to sample these 1 million randomly, I'll get a different average every time. So it won't be a consistent result. And volume. Volume means the total, how much volume of data you want to process. Now the SCV theorem says that you can only choose any of the 2. You cannot achieve all 3. So if you want high volume data to be done with high speeds, you must sacrifice consistency That is because if you really want to process 10 billion numbers with high speed, you must do subsetting, for example. If you want speed and consistency, you cannot do high volume, because consistency means you have to use the whole data all the time. But if your data is too big, then you can no longer do it with high speed. And similarly, you have speed and volume. So if you decide that I want to do high volume data with high consistency, then you have to sacrifice speed. So this is the choice, this is the balance that you have to do. And with that, we conclude the fourth part of this talk. We'll again pause here and then we'll come back to discuss the fifth part, which is big data databases.